Hi, and welcome to 11.1 Current. We're going to be starting our electricity unit fresh off of our electrostatics unit. So just as a refresher, in electrostatics, we talked about charge and charge building up on objects, and it was basically stationary charge. We could transfer charge between objects, but it wasn't really like a flow of charge. And when you had it built up, it created these electric fields. We had a couple equations for electric fields. There was the electrostatic force that you feel. We drew electric field lines, and then we talked about voltage. And we're going to kind of continue by using voltage to talk about electricity, which is moving electric charge. So throughout this unit, we're going to be kind of making an analogy of electrons to water. We talked about this in class. You could think of this as like a wire that's kind of being cut at both sides. Let's draw this side like that. So this is inside the wire. And we have the electrons. It's basically like a metal wire. And in that metal, there are electrons, which are free to move around, and that metal wire is normally surrounded by an insulating wire. And the electrons can be thought of as like water molecules. They move through the wire just like water moving through a river. So the wire is the river, and the water molecules are the electrons. So the first thing we're going to talk about is current. You've heard of water current before. There's also electrical current. You might have heard of that before as well. And it's basically the same thing. Current in a river, as shown below here, can be measured by seeing how fast the water is moving. So the water is rushing through, and it's kind of like a gallons per minute type of thing. That's how they measure it at like hydroelectric dams. They want to see how many gallons of water pass through, let's say, a certain point. How many gallons of water are going to be rushing through this point in a minute. So gallons per minute, common for measuring water current. We're going to do the same thing, but instead of water, it's electrons. So at a certain point, it's like you cut the wire. So how many electrons are moving through that point in the wire in a certain amount of time? So instead of gallons per minute, we'll do, we could do electrons per second, but we're going to use something else. We'll use charge instead of the number of electrons. And you'll remember charge, which is equal to the number of electrons times the charge for each electron, Q equals NE. All right, so how much charge passes through this point in a certain amount of time? So how much charge passes through the point in a certain amount of time, that will tell you what the current is. We're going to use a capital I for current because a capital C was already taken for Coulomb. So I is current. Current is equal to the charge per time. How many coulombs per second? But we don't use coulombs per second. We measure current in amps. All right, so we're going to use amps to measure the current, and this is the formula that we're going to use. I is equal to Q over T. And I don't know, maybe we'll be clever and have to remember this. The charge, Q, is equal to the number of electrons times the charge for each electron, E. This formula can be found in your reference table in the electricity section. So finally, we did this, we did the electric field strength, we did voltage. Now we're doing current. That is a horrible arrow. We're going to do current, and then we're going to do resistance. This is the formula for resistance in a wire, specifically. So it says L is length of conductor. So the conductor would be wire, and A is cross-sectional area of the wire. Anyway, this is just the resistance in the wire. Once we know voltage, current, and resistance, we could bring them all together into Ohm's law. R is equal to V over I. And then we could finally do power. And this W basically stands for work. It's the electrical energy. So work and energy coming back into play. If you'll remember, watt is the unit of power. So like a 60-watt light bulb, yep, that's electricity. So let's get into it. It says if 10 coulombs of charge, so that's going to be our Q. Q is equal to 10 coulombs, passes a given point in a conductor every 2 seconds. So T is equal to 2 seconds. What is the current at that point? So we're still using our guess method, being organized, because as you saw, there's a lot of formulas coming up. So we're going to do I is equal to Q over T. I is equal to 10 coulombs divided by 2 seconds. So the current is going to be 5 amps. Number 2, a wire carries a current of 6 amps. How much charge passes a point in the wire in 120 seconds? So I is equal to 6 amps and T is equal to 120 seconds. They were nice. They could have said 2 minutes, and then you'd have to convert it into seconds because we want seconds always, not minutes or hours when we're using this formula, because we're looking for charge, which is in terms of coulombs. So it has to be in seconds. So I is equal to Q over T. 6 is equal to Q over 120. You cross multiply and you get Q is equal to 720 coulombs of charge. Okay, so number 3 says, how many minutes does it take? Oh, so we're going to pop out an answer that's in terms of seconds, and we have to remember to change that into minutes at the end because that's what they're asking for. So how many minutes does it take 240 coulombs of charge, so Q is equal to 240 coulombs, to pass through a wire in a circuit that has a current of 2 amps. So I is equal to 2 amps, and we're looking for the time in minutes. If you want, you can write it there to remind yourself. So I is equal to Q over T. 2 is equal to 240 over T. And this one's also kind of tricky because a lot of my students just like to cross multiply and they do 240 times 2, or maybe they don't know if they should do maybe 2 divided by 240. Does that sound good to you? 2 divided by 240? Let's see, if we do cross multiply, okay, we're going to get 2 times T and then 240 times 1. So that's equal to 240. And oh, what do? We divide by 2. So 240 divided by 2, not 2 divided by 240. So if it helps when the variable is in the denominator, just write out that extra step, do the cross multiplication, and you should be good to go. So then it's 120 seconds. Oh, there we go. Kind of foretelling there. So to change it, I mean, if you want to get fancy, you could write the number down with its units, multiply by some parentheses, write the units you wrote on the opposite side, then you write the units that you want here, and now you're ready for the numbers to take their place. So 1 minute is equal to 60 seconds, and now we don't have to guess. Do you multiply by 60? Do you divide by 60? In this case, you guys have been doing this probably since grade school, so you know how to convert between minutes and seconds. You're going to do 120 divided by 1. You just basically do 120 divided by 60, and you get 2 minutes. You probably could do that in your head. Listen, this is a good technique to know how to do. You can convert anything this way. So that was a little extra though. Number 4, if the current in a wire of a CD player is 5 milliamps, ooh, that's what that little M, don't ignore that. Just because you don't understand what that is, maybe, don't just ignore it and say 5 amps. The current is 5 lowercase m capital A. So that stands for milli. So the current is 5 milliamps. How long would it take for 2 coulombs of charge, so Q is equal to 2 coulombs, to pass through a cross-sectional area of this wire? There's that term that popped up before. Remember that term? It was in the reference table. So, and it's basically just this. It's this blue region that I kind of highlighted before. So when you have your wire, if you cut that wire in half right here, then it's a cylindrical wire, right? So the area of that thing that you cut, the cross-sectional area, is going to be a circle. And when we do, especially like resistance in a wire, there it is. That's the cross-sectional area. So again, something that just because you might not understand it doesn't mean that you can just ignore it. We are going to have to talk about that later. But right now it's just saying that the current is 5 milliamps and 2 coulombs of charge passes through this region. So there's 2 coulombs passing through there. How long is it going to take for that 2 coulombs to pass through the wire? So the temptation is just to, do our formula, I is equal to Q over T, but beware, it's 5 milliamps. So we have to transfer those. We have to convert 5 milliamps, and let's convert. So milliamps are on the top here, we write them on the bottom down here. We want to go into amps, and let's look. So the reference table tells you that milli is 10 to the negative 3. So this, you could think of it as 1 times 10 to the negative 3 meters is equal to 1 millimeter. Like a small amount of big things is equal to 1 small thing. So that's kind of the conversion factor right there. In this case, though, we're talking about amps. So 1 times 10 to the negative 3 amps is equal to 1 milliamp. So 10 to the negative 3 amps, a small amount of big things, is equal to 1 small thing. And then the units will cancel out, and you get 5 times 10 to the negative 3 amps. And there's a little trick. I don't know if we've done it before, but instead of doing this whole process, which is good to know, but just do it like this if you want. So 5 milliamps, anywhere you see the prefix milli, write in what your reference table tells you. So 5, and then this turns into times 10 to the negative 3, and then you just continue writing what was over here, amps. So the milli turns into times 10 to the negative 3, and you could look at your reference table to do that. It's harder to do the other way. If you want to know if it's 5 amps, how many milliamps is that? You can't really just like switch out the thing like that. But if it's 5 milliamps or even a microcoulomb, so we must have done that before in Unit 10, then you could just do it that way. So you plug in 5 times 10 to the negative 3 is equal to 2 coulombs divided by the time. And our variable is in the denominator again. So if it helps, you could cross multiply. 2 is equal to 5 times 10 to the negative 3 times t. And now you do 2 divided by 5 times 10 to the negative 3 to get t. And t is equal to 400 seconds. And remember, when you're using your calculator, you want to make sure you put this in parentheses or use the E button. So it would be 5 capital E negative 3. Because if you don't, then your calculator is going to spit out the wrong number. Okay, so number 5. If a metal wire carries 80 milliamps, carries a current of 80 milliamps, how long does it take for 3 times 10 to the 20 electrons to pass a given cross-sectional area of the wire? So the current is 80 milliamps, which we just said you could rewrite 80, and then milli is times 10 to the negative 3 amps. And it says, how long does it take for this many electrons to pass? Is that Q? Is that the charge? No, that's the number of electrons. So that's N is equal to 3 times 10 to the 20 electrons. So in order to see how long, so it's asking how long does it take, we want to be able to do this formula, I is equal to Q over T, but first we have to know what the charge is. Really, we need Q equals question mark first. So Q, oh my gosh, that's a G. Q is equal to the number of electrons times the charge on each electron. So the total charge is going to be equal to the number of electrons. There's a lot of them. 3 times 10 to the 20 electrons times the charge for 1 electron, which is still, E, negative 1.6 times 10 to the negative 19 coulombs. That's the charge for 1 electron. So you multiply those two numbers, and that'll tell you the total charge. In this case, it's 48 coulombs, or negative 48 coulombs of charge. Now, the negative number doesn't really matter to us. It's always the electrons that are moving. So really, we just want the magnitude of the charge. And now we know it's 48 coulombs. So we could determine what the time is going to take. So it's 80 times 10 to the negative 3. This is 48 coulombs. And you're looking for the time. Again, cross multiply, write it out if it helps. Just like this. And now you could see you have to divide by 80 times 10 to the negative 3. Really not proper scientific notation. 80 times 10 to the negative 3. Like it should be 8.0 times 10 to the negative 2. But we didn't bother to do this whole process. We just changed the milli into times 10 to the negative 3. And when you do that, you get a time of 600 seconds. Okay, so now it says a total charge of 9 microcoulombs. So the prefix lowercase m still, oh, I said microcoulombs, it's supposed to be millicoulombs. We're not at micro yet. So the charge Q is equal to 9 millicoulombs, which is equal to 9 times 10 to the negative 3 coulombs. It's passing through a cross-sectional area of a copper wire in 3.5 seconds. So part A says what is the current in the wire. Pretty straightforward. I is equal to Q over T. So the current is equal to, you just have to remember this is 9 times 10 to the negative 3 divided by 3.5 seconds. So the current is, as you could see, 0.002, what was it? 57, okay, amps. That's a weird decimal, so I would probably change it into 2.57, and we went 1, 2, 3 times 10 to the negative 3 amps. And look at that, 10 to the negative 3, we could change that 2.57 milliamps if we were feeling fancy. So let's move that over so we could do part B. So part B says how many electrons pass through the cross-sectional area in 10 seconds. So first, what we need to know is how many coulombs of charge passes through in 10 seconds. Then specifically how many electrons. Then we got to do Q is equal to NE after. So part B is actually like a two-part question. So in 10 seconds, we could do I is equal to Q over T. The current stays the same, so 2.57 times 10 to the negative 3 amps. And we're looking for how much charge is passing through in 10 seconds. So you do the cross multiplication and you get a charge of 0.0257 coulombs, which is very similar. It's just another power of 10, right? We multiplied by 10. So it would be 2.57 times 10 to the negative 2 coulombs of charge. But we didn't answer the question yet. Remember, they asked how many electrons pass through. And they're seeing, do you remember the concept of charge and how charge is NE, Q equals NE. So we got to do Q is equal to NE. We know how much charge there is, but how many electrons does it take to make that many coulombs of charge? We're looking for how many electrons, and this is 1.6 times 10 to the negative 19 coulombs. And yes, they're electrons, so we'll make both of them negative, and we'll get a number of electrons by dividing. 0.0257 divided by E. And you get 1.6 times 10 to the 17 electrons. Now, question C is wordy, but there's minimal work that really needs to be done. So it says, if the number of charges that pass through the cross-sectional area during the given time interval doubles, what is the resulting current? So the number of charges that's passing through the wire doubles. So that means that the charge will double. It's the number of charges is doubling. So the charge Q is doubling. What's going to happen to the current? Well, we just put a 2 in the numerator on the right side of the equation. So to balance it out, we need to put a Q in 2 in the numerator of the left side of the equation in order to make it still equal. And so this is just a classic relationship type of problem. You could see the current doubles. And this kind of makes sense if we look back at our river analogy. If the amount of water passing through this area doubles, then the current is getting faster, right? More water is going through here, so it must be moving faster in a certain amount of time. Same thing with the electrons. Now there's double the amount of charge passing through the wire in a certain amount of time, so the current doubles. If you double the charge, the current also doubles in the same amount of time. So that's how you do the calculations with the current equation. You could read through this on the back, take the time and read it. It's kind of nice. Answers a couple questions that you might be having about current in general. Remember, physics isn't just about plugging numbers into the equation. In Regents level physics and honors physics even, it's a big part of it. You got to know how to use the equations, right? But understanding the concepts, that's the key. Have a great day.